Welcome back to the DeFi MOOC. Today we're going to discuss DeFi security. Security is probably one of the most important qualities and properties of a financial ecosystem. If you can't securely transfer or exchange value, likely not that many people will use the system, or it won't be very sustainable in the long run. So let's dive into DeFi security. So when looking at DeFi, you can look at it as an ecosystem that's technically composed of the following layers. So at the very bottom, which I have not visualized here in this very slide, you can imagine the hardware layer, right? And the hardware layer is where your CPU, your computer, your hardware is running, and for example, verifying signatures. So this very layer needs to be secure such that all the layers that build on top of the hardware layer can function in an integrity protected way. Then there's, for example, the network layer, right? You have here the network services such as the domain name services, IP, the internet protocol, BGP, and the peer-to-peer overlay of permissionless blockchains, for instance. Then you have the blockchain layer. The blockchain layer needs to be secure in terms of consensus protocols, for example, the longest chain rule in proof of work. The incentive mechanisms have to be intact. The block reward needs to be paid. The transaction fees have to be plentiful for miners to be incentivized to extend the chain. On the smart contract layer, the blocks need to be well formed, transactions need to be properly signed, and contracts should have ideally no bugs, but as you have already seen in this lecture, there are obviously plenty full of opportunities for something to go wrong. Then there's the virtual machine, so there may be bugs in the virtual machine itself, state transitions might go wrong, etc. On the DeFi application layer, there are plenty of opportunities for things to go wrong as well. So we do have fungible and non-fungible tokens, for instance, ERC20 tokens, as you might have already been exposed to. But there might be ERC20 tokens that are bogus or do have bugs, which again might cause issues in composable DeFi protocols such as exchanges, loans, etc. On the third-party layer, DeFi is interacting with the very traditional UI or website components of the internet, of Web 2.0, if you will. So here, this is really the connection between Web 3 and the traditional internet. And these components naturally have to be secure in order for DeFi to function properly. At the same time, if you're using oracles, so we have had an extensive lecture, a very nice lecture on oracles here, then these as well should be safe and secure. Otherwise, the underlying DeFi protocols, for instance, might make the wrong assumptions. So if you look at an adversary here, this adversary can really attack on any layer, right? He can propose to try to, for example, block the attack the transaction fee reward scheme, or he might disable through some Eclipse attacks, for instance, the peer discovery. He might mess with a DNS service so that peers can no longer find other nodes in the system. He might perform selfish mining. So this is for maybe here on the block and data layer. He might, for example, serve a wrong website, serve just plain wrong JavaScript HTML code to a client that's then being tricked into signing data or transactions that he doesn't want it to sign. So there's plentiful opportunities where an adversary can attack. And the goal today is that we really dive into these different layers and we discuss on each of them what are the possible attacks, or what are at least a subset of possible attacks. Obviously, we can't cover everything today. It's going to be otherwise a very long night, or long day, depending on your time zone. and this is certainly not a feasible endeavor. But we're going to do our best into diving into these different types of security relevant items and explain various attacks along the way. So come on in and jump into the DeFi security lecture. Network layer security. Every blockchain we're aware of, at least the permissionless ones, use some sort of data transmission network, like a peer-to-peer network in most cases, in some cases additional private peering agreements among nodes. And as such, it's really important that every peer is kind of up to date with the data that's being distributed in this permissionless network. So in this segment of the lecture, we'll be looking at network layer security and what are the different things that potentially could go wrong, right? Naturally, this is not an exhaustive list of all the possible network layer attacks, but it should give you a good icebreaker on what's possible there. So if you look at the network layer, we might ask, so why does the network layer matter? Well, we have all the information, like the information about blocks and transactions and even peers, it's being disseminated over the network layer. And this dissemination and propagation is happening in an asynchronous manner. Right? Asynchronous meaning that not all the nodes receive all the information at the same time, and there's also often no guarantee on the bound, on the time delay at which a particular node receives data. If the network propagation is based on IP, the Internet Protocol, then the data transmission is really just the best efforts protocol. So there's no guarantee that your packet arrives even. So that's why we often use something like TCP, so that you have data packet retransmission in order to guarantee that there's the recipient actually receives some data. In some cases, we might have UDP if there's a need for a quick burst of transmission. And in general, there are also more recent internet protocols like QUIC that might be applicable. So I really would like to encourage you to check basically what the latest blockchain protocols are proposing and whether there might be improvements that can be done, which may be a nice research project. So naturally, latency matters. So latency among the peers is really crucial. So if you have a rather larger network, like thousands of nodes, then the latency among those peers matter. So if you're having here one node that's then transmitting a transaction to another node, and this which is connected to a third, or then maybe a fourth node. So the latency, the transmission latency at every hop here really does matter, right? So you want these latencies to be maybe on the order of 50 milliseconds or lower. But sometimes, for example, between Europe and Australia, there might be latencies beyond 200 milliseconds, which naturally then will delay the propagation of this very transaction. Right? So there's an inherent propagation delay from the originator to, let's say, the last recipient of the transaction. Now you might ask, well, how many nodes are there really in these networks? Well, if you look at Bitcoin, there's a beautiful website called BitNodes, where you can see a geographical distribution of the IP addresses of the full reachable nodes. When I say reachable, I mean nodes that have exposed the TCP port 853. This is the default Bitcoin peer-to-peer port. And there are about 100,000. So this does fluctuate, right? Because it's permissionless, you can just spin up your node or shut it down whenever you want. But over the years, over the last, I'd say 4 or 5 years, it's been actually quite consistent at about 10,000 nodes. So these are naturally just the reachable nodes. Reachable meaning, as I said, right, they have an open port. It's highly likely, so if this is, for example, here a reachable node, that there's maybe a light client. So let's assume this is here a mobile phone. So there are light clients with mobile phones, for example, that may connect to this full node. And these light clients, they obviously they don't expose any port, right? They don't service other nodes. So it's really just here these full reachable nodes that have a full copy of the blockchain, by the way. So we call them full nodes. And these nodes are responsible to serving kind of like a deeper network of for example, SPV clients, simple payment verification clients. Now the tricky part is we don't really know how many of these, let's say, lightweight clients there are. And obviously there can also be full nodes that are not exposing their IP. They can still be connected here to these different nodes, but let's assume I draw them here like in a shallow circle. So let's assume these are here nodes, they're connected somehow in this graph, maybe like this. So, and they are not exposing any TCP port, right? So no open port. And for these nodes, we can infer that there are some techniques actually that may infer that there are these nodes. There's, for example, a paper called TX Probe that I can recommend you to read, which is quite cool. It's a cool technique to also infer the topology, like which node is connected to which node, right? So there's a lot of work basically on the network layer of identifying who's connected to who, etc. But what we know is, well, long talk, short conclusion. We just know like there are these number of publicly reachable nodes that you can look at. So I'll leave it to you as an exercise to check out the number of publicly reachable nodes, for example, for Ethereum or your favorite blockchain, such as Dogecoin or whatever, to see what's your number of full node. Notice that this number of full node doesn't really imply anything on the sense of decentralization. It's not really, these nodes are not doing any mining, or not necessarily doing any mining. So it doesn't immediately affect the security of the network, but obviously there shouldn't be just like 3, right? So, well, 3 being just a magic number, which doesn't mean anything per se, but I hope you understand what I mean. You want this number to be reasonably high, that there's enough redundancy. But now whether we have 10,000 or 20,000, I'm not sure it does make a big difference on the decentralization of the network. There are likely other factors that are more crucial. So I already answered this question here to some degree. So we do have these full nodes, right? These are full nodes that host basically the entirety of the blockchain, and the light nodes that might, for example, just host the chain of headers, just the block headers, while omitting the transaction content. A header in Bitcoin is about 80 bytes in size, so that's a rather small amount times the number of blocks, and you can calculate how big that would be. And then in order to verify whether a transaction is included in a block, you can run the SPV protocol that we discussed earlier in the lecture to verify whether there's a transaction actually in the block. And so these light nodes here often communicate with the full nodes, and they're really dependent on them, right? So you have the light nodes, depending on your client, connecting to between 5 to 10 full nodes and requesting data from those. So you might ask now, good, okay, I got a high-level understanding of what this network looks like, but how do transactions propagate? Well, let's assume here we have this world map of just like 2 miners and a few nodes, a few full nodes. That's just if you assume we have full nodes, so no lightweight clients here in this particular figure. And we have a trader, he issues a transaction and he's willing to pay a transaction fee of 5. So for the time being, we ignore what value that 5 represents, or what unit this is. It's just like an absolute number 5 here. So then this transaction propagates, because it somehow propagates to one of those miners. And this miner has an internal queue, so it's called the mempool, or memory pool. It's basically a term stemming from Bitcoin, and other blockchains adopted that one, where you have the list of unconfirmed transactions. Unconfirmed meaning this transaction was not yet mined in a block, right? So you do have for example, here already 2 transactions in this memory pool. One is paying a fee of 1, the other one is paying a fee of 10. So if we add this third transaction, right, then the order in the final block that the miner would be mining could be the following, right? So the transaction that gets executed first is the one that pays the highest fee. So the execution order here would be then along this basically in this direction, right? So you have here transaction number 1, which pays 10 fees, transaction number 2, which pays 5, and transaction 3, which pays transaction fee of 1 only, right? So this is, we've looked actually at the Ethereum blockchain a few months back, and this is back then roughly what 80% of the miners were adhering to, right? This is the transaction fee order, or transaction gas fee order. There are naturally other agreements, private agreements, other ways to pay miners that are where miners have become, and the community has become really creative recently, which is amazing to see. But in essence, at the end of the day, it's likely always the transaction that pays or rewards the miners the most will have the highest chance of being executed first. So what does that mean? Well, from a security perspective, because this is the security lecture, we have to look at here an attacker. So what could an attacker do given this knowledge, right? Well, the attacker could create a so-called spy node, meaning a node that's connected to as many peers as possible, being here these full nodes as well as miners, if the attacker can identify the IP addresses of the miners and nodes of the miners, obviously. But the attacker can really try to connect to every node, right? And we have seen dedicated clients doing that. So things they do is basically optimizing the internet connectivity in terms of the latency, in terms of the upload and download bandwidth, in terms of the co-location to miners. So it might not even be only one physical spy node, but several physical spy nodes. For example, what we've seen is that the AWS networks are a really popular place to host, for example, Ethereum nodes. And naturally, if you as an adversary, you're being co-located in the AWS data center and you're connecting to the nodes in that data center, you will have the quickest connectivity to those, right? So the attacker will certainly need to deploy basically several high-frequency peers, spy nodes, if you will, in the globally to have a complete picture of what's going on the network. This is just a network layer, right? We are not yet at the blockchain layer where data is actually written into the blocks. All right, so given this knowledge now, so let's assume we have here an adversary with a spy node, and naturally, because the adversary is so well connected, he will receive, or he will get notice of this transaction that's being sent with a transaction fee of 5. Now, we've earlier discussed that we have here a mempool, right? The pool of unconfirmed transactions of the miner. And what the adversary can do, because the adversary has a direct connection to the miner, so he can actually probably speed up the propagation of the victim transaction here of the 5 of the blue of the blue transaction with transaction fees 5 by simply creating a transaction that pays like one element more of transaction fees, and the adversary can even like ship the victim transaction to the miner. So, I mean, why would he ship the victim transaction as well? Well, it could be that the victim transaction is being stuck somewhere, but it's important for the adversary that the victim transaction remains close to the adversarial transaction here, the red one, right? So let's assume these two packets beautifully arrive at the miner, and then what you see here is this order, right? So you see, all right, so there's a transaction fee 10, 6, 5, and 1. So the execution order will be the following, and we just said that this here is the adversarial transaction, right? And this here is the victim. So we can see here that the adversary is front-running the victim, right? Front-running in the sense of attempting to be executed before the victim, while basically acting on the information that this victim transaction is propagating in the network. So there are different definitions of front running, which may also have different legal implications. I guess I'm not an expert in that field, but the SEC, for instance, defines front running as an act of operating on private information in many cases, as far as I've understood. So here you might say, well, the knowledge that there's a victim transaction propagating isn't really like private knowledge, right? I mean, this is a public peer-to-peer network, everybody can connect to it. So some might argue that this is maybe not a definition of front running according to some legal understanding, but I'll leave this to the regulators and lawyer to fully understand and capture. And just want to show you here that there's certainly the possibility of replay of altering the order at which transactions are executed on chain, which has a significant impact on DeFi in as we will see in later sections, specifically when we speak about sandwich attacks. So front running is really like an important property. I can recommend you check out the paper Flash Boys 2.0. So Flash Boys was a high frequency trading book many years back, and Flash Boys 2.0 is kind of it's kind of the first paper that discusses one of the first papers that discusses front running in the public permissionless peer-to-peer networks of blockchains. Similarly, we have front running, but we do have back running. Right, back running is basically the same process as front running. However, the adversary tries to be executed right after the victim. So, for example, if there's a price oracle update and you want your transaction to be executed right after the price oracle update, you might back run the price oracle update, right? Because you're aware that there will be a state change upon the successful completion and execution of the oracle transaction. And hence you can immediately, for example, liquidate a lending position. So the process is again the same, right? So here there's a victim, issues a transaction with transaction fee 5. The adversary visualizes or finds this victim transaction. Let's say it's a price oracle update. Then the adversary will issue an adversarial transaction paying the same gas fee or same fee, depending on your chain, obviously, so same fee. And then what matters here is the order at which these two transactions arrive in the mempool of the miner. So if the adversary makes sure that the victim transaction is sent first and then the adversarial transaction is sent to the miner, in that case, as far as I have understood, Geth is currently ordering transactions in the following way. So for transactions that pay the same gas fee in Ethereum, the one that is received first gets executed first. Right? So you could obviously also pay a fee of 4 if you'd like to. However, if there's another transaction that pays 5 and arrives later, it might get executed before your backrunning transaction, which you maybe don't want to. So in a sense, the order of transaction execution is again the following. And here we have this time the victim first and then the adversarial transaction afterwards. So yeah, as I mentioned here, this can be a liquidation, while the adversarial transaction, the victim transaction can be an oracle price update, for instance, right? Because based on this price oracle update, you can infer, well, I know that this debt position will be liquidated after the execution of this price oracle update. Hence, I want to be the first liquidator and grab the liquidation profit. So you've seen, right? I mean, there's so many things going on the network layer. You can front run, you can back run transactions. You have to consider with which nodes you peer with which nodes you do not peer with, maybe even how to co-locate, in which data center to co-locate. How do you manage your TCP connections? I mean, think of setting up like 10,000 of TCP connections. You probably need to increase the file descriptor size on your Linux machine. So there are really like a lot of network layer security aspects that you need to consider when doing front running or back running or in general blockchain security. So very exciting. Welcome back. One of the most dangerous network layer attacks are Eclipse attacks. An Eclipse attack is in essence something where you exclude a peer or a group of peers from the entire network communication. So it's really a dangerous partitioning attack in essence, where some peers might no longer receive the latest transactions. They may no longer know what's going on in the network. Did I receive transactions or not? So it's a very impactful attack with a lot of consequences down the line. So let's jump into it. So if you're looking at Eclipse attacks, it's always easy or easier, let's say, to visualize the network. How does the network look like? How do peers communicate to each other? And how does the information propagate to the peers? So let's assume we have here the leftmost node and it's propagating a transaction or a block along this network. And well, it seems like one of these peers is actually malicious, right? So turns out that's our bad guy today. Now, this bad guy chooses to not forward a transaction or block to the rightmost victim here, and hence this victim is really eclipsed, right? This is very much the definition of an Eclipse attack. So Eclipse attacks in permissionless blockchains, in particular Bitcoin, were first introduced by Heilman et al. At Usenix in 2015, which was a seminal paper that describes Eclipse attacks in general. But to carry out this attack, there were like a lot of requirements, right? I mean, the adversary had to monopolize all the connections, as is the case here, right? So our victim here is only connected to one node, which is, well, bad luck, an adversary. And there were also the requirement that the adversary here spams the IP address information, so spans the number of addresses that the victim can connect to, so that the victim would only connect to the adversary. The node had to restart, which is quite a strong assumption, and obviously because of this construct, it required many bots, so many IP addresses that the adversary would control. Later, quite shortly after, actually, there were more attacks coming by, Eclipse attacks in particular, which have shown that it's actually enough if there's just one connection to the victim and we don't require the victim to restart. So there are actually ways to perform Eclipse attacks by exploiting the network propagation mechanism. So how data is propagated, right? So because here, for example, you need to have some communication protocol of how this transmission is done. So by exploiting this communication protocol itself, we can perform Eclipse attacks. So Eclipse attacks in general have dire consequences on a security perspective. So one is a danger of denial of service, because this node is no longer receiving here transactions from the network, so it cannot process or receive any payments. As such, it's no longer able to service, so that's why it's a DOS. And the other problem is that it allows us to create double spending attacks, where the adversary can trick the victim into accepting a transaction that might be conflicting with another transaction or n other transactions in the network, hence the term double spending. All right, but let's first look into how we can create Eclipse attacks based on the exploitation of the network propagation protocol. So as I've mentioned at the beginning of the lecture, information is mostly propagated over the Internet Protocol. It's a best effort protocol, and as such there's no guarantee that data is received at a given time. And therefore most blockchain peer-to-peer protocols that I'm aware of have so-called request timeouts. So how long do you wait for a peer to actually send you data? And these request timeouts can be static, which is most often the case as I've seen, but they could be technically also dynamic, and that would probably be quite beneficial for some of these protocols. But let's assume now we have here an adversary, and the adversary is advertising the hash of a transaction or block to the victim. So in Bitcoin, this is a common way to advertise to the victim, I have a transaction or block, and this transaction or block, they have the following hash. Now, the victim here in this case will then request the data from this adversary. And even if there's another peer that at the same time advertises or shortly after advertises the same transaction or the block, the victim will in the first step, request this transaction or block from the adversary. And only if the adversary doesn't reply, given a certain request timeout, then the victim will request the data from another, hopefully benign peer. So in Bitcoin, we have a block timeout of about 20 minutes and a transaction timeout of about 2 minutes. So as an exercise for yourself, I leave it obviously up to you to check out other chains, how they're propagating data, what are the request timeouts. So I think this is quite an intriguing exercise for you, and I'm almost guaranteeing you that you will find some security relevant issues there. So what are the security implications if we have these timeouts here specifically in Bitcoin? Well, there was the possibility to blind a victim from blocks and transactions for more than 20 minutes in Bitcoin. I've done an experimental validation, so this was actually tested in a local test network, and the impact from these Eclipse attacks that are really purely based on the propagation medium is that you can perform easier double spending transactions, you can exercise aggravated selfish mining, and even network-wide denial of service attacks were possible at some point. Luckily, this did not happen. So there are a few mitigation techniques that we can also discuss, but basically there are hardening measures that are possible. For example, you can make the timeouts dynamic depending on the latency with your peers. You can request data from multiple peers, and you can basically estimate then how long you have to wait in order to be relatively certain, so which you can quantify in probabilities, that you have received a transaction. But let's dive into the Eclipse requirements of these attacks in particular to fully understand the attack. So the very first requirement is that the victim must receive an advertisement from the adversary first, right? So that the adversary is really the first peer that advertises a transaction or a block. So for example, if the network here is advertising a block to the adversary, then the adversary will advertise this block or transaction to the victim, and the victim will say, okay, great, thank you. I will wait for you to send me the object that corresponds to this hash. By object, I mean now the transaction or block, for instance. And naturally, at some later point in time, the peer-to-peer network or the other connections of the victim to the peer-to-peer network will advertise the very same transaction or block. However, the victim will, in most cases, or at least when following the protocol, will wait for the adversary to transmit their data. So, ideally, in order to perform an Eclipse attack on the network propagation protocol, through the network propagation protocol, would be by having a timeout, ideally, as was in Bitcoin the case, a 20-minute block timeout and a 2-minute transaction timeout. So now, how likely can we be the first node on the network? I mean, what's the likelihood of achieving that at all? So what we've done is a little experiment. So we've spun up a node in Zurich that is highly connected, specifically to the Bitcoin network, and then also to our victim nodes in California, Singapore, and Frankfurt. And we changed the number of connections that the adversary was running. So we had 40 connections, 80 connections, 200, and then 800 connections, right? So we had the adversary basically operating a variety of different connections here. So naturally, you might think, well, if we're running 800 connections, that's quite a lot. That's much more than the default average that we found at the time to be roughly 40. And so we've also seen that if you're operating that many connections at the time, you had a nearly 90% chance of being the first node in being able to advertise a hash, right? So here the Bitcoin network basically advertise an object to our Zurich node, and then we would advertise this object to our victim nodes, which have all 40 connections in this example. So, and if the adversary had 800 connections in the network, then we had a roughly 90% chance of being the first to advertise the transaction or the block. So that's great, right? This is the first requirement. So if we are playing well on the network layer, then we're having a good chance to be the first node there. And obviously later on, these transactions are being advertised to our peers, but that doesn't matter anymore because now the peers are just waiting for the adversary to transmit that data. Very good. So now we have on the network layer, we need the timeouts, right? So what happens if we are the first to advertise a particular transaction or block? So on the transaction layer, there is in Bitcoin, there's a first in, first out queue, FIFO. So what an adversary was able to do, I haven't verified now recently, but this was possible, and we verified in practice that you can send a transaction hash multiple times to the victim, and here in this case, if it's sent 3 times, there will be already a 6-minute timeout. So you can basically stall the victim completely from receiving a transaction because of this relatively bad or unfortunate design of a FIFO queue. So for all the versions of Bitcoin, so luckily this was fixed after we published this attack. So for all the versions of Bitcoins, it was possible that after 20 minutes, there's a disconnect of the node and it does nothing. And so we've actually shown in the past how it's possible to do indefinite block Eclipse attacks in Bitcoin because due to the network propagation protocol. I will spare you the details because luckily this is fixed by now, but this is just an example to show you that the security on the network propagation layer is really tricky to get right. And later on it might have dire consequences on the security of the underlying chain and the users as a whole. So I hope you like this lecture on Eclipse attacks that work both by just basically brute forcing your connections on a peer, or by exploiting in a very nifty and clever way the propagation mechanism that might not be that ideal. So as a homework, you might ask yourself, why would a peer only request data from one peer at a time, right? Why would the node not for example, request the data from multiple peers at a time? What's the rationale behind that? So if you have an answer, please leave a comment down below or give us an answer in the chat. Would be very much appreciated. Welcome back. We're going to now discuss blockchain layer security. So this is the layer where you have blocks and how you chain blocks. So you have a blockchain. So how you build this very chain is basically the topic of this segment today. So the interesting aspect, and pay close attention to this, is that the previous lectures, for example, the Eclipse attacks, can actually be combined with attacks on the blockchain layer. So let's dive into that. So you might ask, why attacks on the blockchain layer? And well, I'll tell you, it's because they're really interesting. You can do particularly, for example, double spending attacks. Maybe you've already heard of it. You can also call them N spending attacks if you can spend a coin N times, right? And in essence, Bitcoin really solved double spending issue on an internet cash basis. Then there's selfish mining. It's a really brilliant idea that was presented a few years back. There's undercutting and there's bribery as well. So we won't go into all details, but it's just I would just want to basically give you a little bit of an icebreaker for you to understand what are the implications of blockchain layer security. So the first example that we dive into today is double spending. So double spending is a process whereby the adversary is able to spend a coin more than once. Right? So this is, for example, possible if an adversary is creating a transaction that looks legitimate to a vendor. So we have here the victim or the vendor V, and the adversary is sending a transaction to this particular vendor. At the same time, the adversary might be sending a double spend transaction to the public peer-to-peer network, where miners then picked up this very transaction. So if the vendor is accepting so-called zero confirmation transactions, so transactions that were not confirmed in the block, but just basically delivers the goods or services to the adversary here upon the reception of the legitimate transaction. Then the victim is susceptible to double spending attacks. So naturally the vendor will try to forward the legitimate transaction to the network, but since there's an inherent time delay between the adversary's double spend propagation and the legitimate transaction propagation, it's highly likely that the legitimate transaction will be invalidated by the majority of the network. And that's because the legitimate transaction and the double spend transaction are conflicting, so they cannot be mined both at the same time. And this is really just the process of double spending, right? I pretend that I have a coin here that I can spend on a good or services, and in reality I actually do spend this coin elsewhere. For example, I do send it to my own address, right? So a very traditional double spend. Eclipse attacks are at the very core of how you can perform such double spending attacks, which we've seen in the previous lecture. So you kind of have here a semi or a partial eclipse attacks because the vendor doesn't know about the double spend transaction, so it's kind of like eclipsed for a period of time from this real network where the actual transactions are being spent. So another blockchain layer security issue is selfish mining. And we will look at selfish mining also with an Eclipse attack, but let's first discuss what selfish mining itself is. So that's an idea from Ayala, a really seminal paper and seminal idea that that basically explains how to publish or not publish a block, so to keep a block private in order to gain a financial advantage in the network, or specifically in order to increase the mining power in the network. So the goal is that other miners will perform wasteful computations. So you can look here at this state transition function or state transition graph that we have. We denote by alpha the hashing power of the adversary, and by gamma a network layer propagation parameter. So the stronger the parameter, the better you can propagate data. So for example, right, so we have the probability 1 minus alpha that the honest network is mining a block, right? So this means that the adversary will have an advantage of 0 blocks over the honest network. However, if the adversary has a hashing power of alpha, then with probability alpha, he will mine 1 block, which is not yet public. So that's a block that the miner will just keep to itself. It will be private in essence. And then there's a likelihood 1 minus alpha that the honest network will find a block, right? So in essence, you can look at the blockchain as such. So this is here the first block. And then let's say the adversary is mining 1 block, right? So this is with probability alpha. And then the honest network is also mining a block at the very same height, because the adversarial block, right, this one here, is not public. So the honest network doesn't know that this block exists, right? So now we're in the state 0 prime because we are at the same height, right? So here there's like just 1 block kind of distance. And then it really depends what the adversary is going to do. So if the adversary is mining a block with likelihood alpha, so that would correspond to this case here, then the adversary can publish those 2 blocks and effectively kill this prior block, right? So then then the honest network will continue mining on this one, and the adversary as well. So we are back to square one, to the first start. But there's also the likelihood that the honest network will find a block, right? And depending on the propagation parameter alpha, which is the network propagation, it's unclear on which chain the honest network will mine. So let's start again from the beginning here. So we have this block, right? So we have the adversary. He is mining this particular block here. And then there's the probability 1 minus alpha that the honest network finds a block, right? So this is this particular block here. And at this very moment in time, this block will start propagating in the network. So the adversary has a choice. Well, he could just choose to publish his currently private block, right? And therefore, the propagation parameter here of the honest network, how this block will propagate, influences the likelihood of which block will win, right? Whether this is the adversary block or the honest network block. So hence the two cases, right? There's one's the override case where two blocks override one, and there's the other case where the network propagation parameter will decide on which block will win eventually the race, the mining race here. Good. So we did cover now all these cases here. And the remaining cases, they're rather simple. So here alpha is the probability that an adversary finds a block. So he's one block ahead in his private chain. Another alpha here would bring him to two private blocks, etc. Right? And so this 1 minus alpha indicates, for instance, if the honest network finds a block, 1 minus alpha, well, the adversary could publish both of his private blocks to override this public network block. But once we are here at 3 or 4 blocks, we can actually jump back just like by one block if we want to override that particular victim block. So we don't have to jump back to 0 if we don't want to. So this is a rather interesting state machine here that we have, right? Just for clarity again and for repetition. So this number here, 0, 1, 2, 3, etc. Quantifies the number of private blocks that the selfish miner is currently having, right? That the selfish miner has amassed. Note that alpha is always assumed to be smaller than 0.5. Hence, the likelihood that you will get 4 or more private blocks in a row is quite small. But yeah, the probability is not 0, and it depends really on the hash rate and kind of luck in that case of the selfish miner. Very good. So we have come quite far. Really good job. So continue on grasping the details here of selfish mining. It's a really super exciting topic. And we're gonna go a little bit higher on the level of complexity. Now we're gonna combine selfish mining with an Eclipse attack. And what you can see here is we have the very same state transition as before, right? If you remember from the previous slide. But now we're gonna add another variable p. And p is the probability to eclipse a block to a miner. So basically to hide a block towards a specific miner in the network. And we're not going to go into the full details here, but I really would like you to understand the intuition that once you can combine an Eclipse attack with selfish mining here in this particular case, you can kind of create different realities, right? You can have some fraction of the network being on one side and some other fraction of the network being on another side of reality, really, because by partitioning the network, by creating Eclipse attacks, you're preventing peers from receiving data. Hence, for them, the reality looks different than to other peers, right? And this is at the very core of security, or basically fraud in distributed, decentralized ledgers when it comes to miners. So you might ask, well, I mean, in practice, do we observe selfish mining at all? And there's so far as I know, no scientific work that has proven that selfish mining was in fact practiced by miners. I think an empirical study might show the statistical significance of the block generation times and might give indications of whether there is a change over time on the habit of miners, so how they publish blocks, but I haven't seen any study on this, and this would be certainly very valuable future work. And even then, I think it's really hard to find a proof. So to find an irrefutable proof that that selfish mining is being performed, just due to the fact that this is an attack that's possible by hiding data and just publishing it selectively when it fits best. And there's no way to prove that a miner found a block early on. So this is just it's a tricky thing to prove, basically, that a miner performs selfish mining. While Eclipse attacks obviously are more visible as an attack, but yeah, maybe maybe some of you will perform in the future, or have some ideas in the future on how to prove that selfish mining was performed. So I'm really looking forward to that. So now we want to look into the implications of selfish mining. So what is selfish mining? What's the result of selfish mining? So on the x-axis here we have the pool size. This is the hash rate or alpha that we had previously. On the y-axis we have the relative pool revenue. So this is the revenue that the miner receives based on the pool size and based on the Eclipse attacks or selfish mining strategies that the miner performs. Right? So let's assume here, let's look just as honest mining at the very beginning. So honest mining is this green line. So this is the best case scenario, right? Nobody is malicious. Everybody basically follows the honest protocol. So for instance, if you have 40% of the hash rate, so you can read the chart as follows, you go here up, 40% of the hash rate, well then I get 40% of the revenue, right? Sounds fair, right? So it's a linear relationship. Now, if you start to perform selfish mining and the propagation parameter is set to 0, so this means the honest network has a bad propagation parameter, then you can see that the revenue is all right, but we can see here that I mean the revenue here is actually below the honest mining revenue, but we can see there's a threshold, like maybe roughly 33% of the hash rate, at which, well, I mean, if we have 40% of the hash rate, we're here nearly at 50%, so maybe 48, 49% of the entire hash rate, which is quite alarming, I would say, because this means we have made a plus roughly 8% increase in the revenue. And it's not an increase in revenue, but we have a 48% revenue despite only owning 40% of the network, which is super dangerous. And as you might know, once we go beyond 50% of the relative pool revenue, we basically own the chain, right? Because we have a majority voting right, so we can double spend and outrun basically any honest player. So if the propagation parameter here is 1, right, we can see that even at we basically only need about this is, let's say, 38% roughly. So I haven't checked the numbers specifically. 37 to 38%. Basically, we own the chain. 50%. Right? So this is quite alarming. So obviously, we know that a propagation parameter matters to increase the likelihood of an Eclipse attack or a selfish mining attack in this particular case. But now if we go beyond the standard selfish mining attack and we add an Eclipse attack, so we have the 50% chance to consecutively deny 2 blocks to a miner, right? So this is P. In that case, we can even lower the threshold. So we're here now at maybe 34%, right? So if we get 34% of the hash rate, then we can own the chain because the relative pool revenue will be 50 or above 50%. Right? And this is really at the very core. This is very core blockchain security, and a parameter that we really have to understand where the blockchain starts to become insecure. So it's certainly the threshold for secure blockchain is not 50% of the hash rate as many assume, but significantly lower, probably on the order of 30 to 40%, as we can see in this very chart. So I hope you like this intuition on blockchain security, and especially this this subtle notion of how we can combine various attacks, right? So we combine this attack on the network layer with the blockchain layer, so the Eclipse attacks and plus the selfish mining attack. And if you're an adversary, you can have fun and you can poke at decentralized blockchains by doing so yourself, right? You can do a selfish mining attack, an Eclipse attack, and probably a DeFi flash loan attack on top. So it's really like just like how DeFi is a Lego, where you can plug in a different finance concept. Well, on the security side, it's the same. It's really just a Lego, and you can play around. Welcome back. We're gonna now discuss smart contract layer security. And as you already realized, right, we are going slowly up the different layers in distributed ledgers, and hopefully soon arriving at the DeFi layer. So the smart contract layer is the layer where you write smart contracts. Like, for example, the following here is a contract written in Solidity. It's a contract called a wallet. It does have a state variable, which is called a balance. It's an unsigned integer, and it's initialized here with the value 10. This smart contract also has a function. It's a function called withdraw, and it can perform apparently a withdrawal if the balance is bigger than 1. So then it can basically send a value to the message.sender, which is the address that is actually calling this very function, and it will send a value which is it will basically send the entire value that is written here in this variable, state variable balance. Afterwards, once this is sent, the balance is zeroed out, is set to 0. Well, I mean, you already know that smart contracts are programs that handle money, executed on the blockchain, written in this high-level Solidity language, and then compiled to VM code, for example, EVM code for the Ethereum virtual machine. The smart contracts can typically be trusted in the way that they are not. It's not possible to patch them after release, but you can still have functionality that obviously changes its logic. So yeah, what can go wrong, right? We have code handling billions of US dollars. Not much can go wrong, I guess, right? Well, as you have already seen, here there are the ways to basically transfer money to a caller, right? And this caller can be anyone, and this being anyone really sounds like a bad idea. And as you have already seen in other lectures, that getting security right is a really challenging endeavor in DeFi or decentralized ledgers in general. So we've witnessed a variety of DAO attacks, of attacks in general, actually. But the DAO attack was probably one of the most famous attacks, where there were like a significant number of funds stolen. EtherDice, which was one of the very popular gambling sites, was down for maintenance as it had issues, security issues. The Ether Throne had issues. And the list is going on. I mean, I think we've counted, at least in 20 or 2021, over 90 or probably wide over 100 DeFi incidents in those 2 years. So they're literally like millions and millions of US dollars were stolen. So getting security right, especially in the smart contract layer or in the DeFi layer, is very challenging. So let's look at one of the most famous security attacks, which is called the reentrancy attack. We do have here a wallet contract. The wallet contract is the one that we've just discussed in the earlier slide. And let's assume now we have a user contract. So the user contract is the contract that will call the wallet contract. And specifically, the user contract has a function move balance, which will call wallet.withdraw, which is this very function here. Right. So technically, we just want to call this withdraw once and get, for example, the 10 Ether back. And there's a value of 10 here, right? So that shouldn't be that complicated, right? But what about later? So if later we call withdraw again, there should be no transfer, right? Like the balance should be zero. There should not be any additional funds that are coming out of the contract. Well, the question is really here: can the user contract withdraw more than 10 ether of the wallet contract? So I would like you to pause maybe the video quickly, or think about this, and or maybe you can even you can comment in the chat. So is it possible? Yes or no? And please also mention why it might be possible or why it might not be possible. Okay, so if you look here at this very call function here, right? We have message.sender.call, which transmits the value that's specified in the balance state variable. Well, this very function here may implicitly call the so-called fallback function in the user contract. Here, this is the fallback function. And in this callback function, you can execute some code, right? And only after this very code, the balance will be set to 0. And that's naturally quite an issue, right? When you code smart contracts, because this this fallback function here might call again the very same contract. So let's look at how this works. So here, basically in this, you explicitly now define the fallback function in the user contract, and in that fallback function, you basically call wallet.withdraw again. Right? So this very function here will be called again and again and again, and this will be executed, but the balance will not be set to 0 because the execution is still running. And an adversary stole with this type of attack over 3.6 million ether in a particular attack. So reentrancy was and still is a major instance of smart contract vulnerabilities. So let's look at the security bug number 2, which we call unprivileged rights to storage. We do have a wallet contract here with a function init wallet and a function withdraw. So the init wallet function allows you to set the owner. Here, owner is an address, and it's a state variable in the contract. And the function withdraw is basically the function where you can send the amount of money, for example, that the contract has in this very smart contract. Now, what is wrong here? Can you tell me, what do you think is bogus about this contract? So again, please pause the video quickly or answer in the chat with any ideas that you might have. So if you look at this particular line here, only the owner can send ether, right? So there's a security check, access control check, very good. However, here, any user may actually change the wallet's owner, because any user can call the function init wallet. There is no check on who is eligible to call the function init wallet. Hence, you can basically just set yourself as owner and then withdraw the entire amount in this contract. You see, getting smart contract security right is not an easy feast. So an attacker basically used this or similar bug to steal over 32 million US dollar at the time. So let's move now on to another smart contract bug exercise. So we have here a contract which is called example, and we do have two state variables. We have an address it's called the owner, and we do have another state variable which is called my secret, and this one is private, right? We do have a constructor in this very smart contract, which is good because it sets the owner to the one deploying this very smart contract. We have a function set secret, and we have a function get secret. So again, can you tell me what is conceptually wrong about this smart contract, right? Why is this not a good idea? Okay, I'll give you a little hint, right? So who do you think would be able to read my secret? Absolutely. So any variable is basically readable on the public Ethereum blockchain, right? Whether it's called private or public, it doesn't matter. It will be readable. So declaring a variable as private only restricts the automatic creation of getter functions for the variable, but it does not hide the content. So please don't be fooled by these keywords, these solidity keywords that are certainly not implying that this my secret value here will not be shown or somehow occluded or somehow encrypted. There's no encryption going on here. This is literally just an access control parameter for when you, or a visibility parameter when you look at the smart contract, but it has nothing to do with the confidentiality of this my secret variable. So really be careful regarding those statements. Obviously, you could argue that's not a bug. It's just how solidity is defined. But we understand here a bug, meaning that the programmer understood that my secret is actually a private variable, while it's not. Let's move on to smart contract bug exercise number 2. So here we have a contract called vulnerable. Now we do have here 2 state variables, one authorized and one balance, right? Which are mappings from an address to a bool, to boolean, and from address to an unsigned integer. We do have a function called refund, and we can specify here an amount that's an unsigned. There are a few security checks. So here it requires that you're basically authorized. And so the message that sender is authorized, or part of this authorized mapping. And it's required here that the amount is small or equal to the balance of the sender. So you cannot withdraw more than your balance currently amounts to. And then there's a message.call value. So we've seen this is it's an example that we've seen, and afterwards the balance is deducted from the amount that you withdraw, right? So would sound quite normal. So what's wrong with this exercise here? What isn't very clear? Please write in the chat or think to yourself, and you can also write comments down below. Okay, I'll give you a few more seconds. All right, so I give you a little hint. So who can be message.sender really when calling the smart contract? Well, anyone can be message.sender, right? But the bigger picture here is that the code is, again, vulnerable to a reentrancy attack, right? So the balance of message.sender is only updated at the very after we have actually transferred the amounts, right? After the transfer is made, which is a really bad design. So if the message.sender is a contract, so it's a user contract as we've seen before, and has a fallback function that calls again in the refund function here of this vulnerable contract, then message.sender can actually deplete the contract of the funds. Very good. So how would you exploit this very smart contract? Can you pause the video quickly or propose basically where you code, what code you should write? So specifically, it's here and here. So the hint is, please check the previous message. And naturally here, right, we have V, which is the vulnerable contract. We are the exploit contract or user contract if you go back to the previous exercise. And we have here the exploit function that will call the refund. And we define a fallback function where we do the same, v.refund, the same amount. And given that, we can simply drain this very smart contract. I would like to focus, basically also clarify here that these balances here are state variables, right? Because the smart contract itself has a balance that's specified by the EVM, and these variables here are custom balance variables, right? These are not given by the EVM. So there's a clear difference between the EVM balance of a smart contract and the balance of a smart contract as defined by its state variables. Okay, very good. There are many more smart contract security bugs that you can find, and maybe some of you might even find new types of bugs or security issues. So there's unexpected ether flows, insecure coding, unsafe inputs, etc. So I can also recommend you to look a bit online in the various resources that you can find. For example, here Consensus has a great document on explaining various types. And you might still ask me, well, how can we prevent, or how can we identify where smart contract security issues exist? Well, the issue is that if these are all the possible contract behaviors, if you map this on this 2D plan, then there might be a few bugs in there, right, which we might not see. So these are kind of security bugs that might be relevant from a financial perspective. So the underlying problem is we cannot enumerate all possible contract behaviors. So we need somehow a clever way of finding those security bugs. On a very high level, there are the three main methodologies on finding bugs is testing. There's a lot of manual testing involved in particular. Auditing companies are doing this quite well nowadays, but naturally they don't find everything. There's the dynamic analysis or symbolic execution, and there's also the static analysis or formal verification even. And you could say on a very high level, right, that testing is like finding or trying to find a few things and might find a few bugs here and there. So it's easy to implement. It's just a lot of time and resource intensive, but might yield only very limited guarantees. The dynamic analysis might yield some better coverage, I would say, of the contract. So it's certainly better than testing, but it can still miss vulnerabilities. And static analysis or formal verification might provide stronger guarantees, but it also suffers from many false positives. So it might be actually tricky to identify a bug in the reports that you find. And naturally, if your formal model is wrong, then you also have an issue here. So I hope you liked this lecture on smart contract vulnerabilities. Go out maybe on Etherscan and try to find a few smart contracts and their associated code. Go look in there. Maybe they do have some issues on the authorization side, so they don't require the owner, or you can set the owner if they basically miss modifiers. Or maybe they do have some vulnerabilities, some reentrancy vulnerabilities if they use the call function to transfer assets and only later on update the balance. So go out there and start hunting. Welcome back. We're gonna now discuss DeFi attacks and focus in particular of flash loans, or how flash loans can be used to carry out attacks. Notice that a flash loan is really just a tool. It's not the attack is not just a flash loan attack. It's an inherent issue of the design of a DeFi platform. But a flash loan makes the attack execution particularly simple and cheap. Please, if you're unfamiliar with DeFi flash loans, look at the previous lectures where we discuss how flash loans operate. That's certainly necessary knowledge required to understand the attacks that we're discussing here. So what can go wrong, right? You have access to billions of capital by just paying for a little bit of transaction fees and minor percentage of interest rates. So what can possibly go wrong? So we've seen that many DeFi attacks are really kind of using flash loans, these instantaneous loans of a significant size, to carry out attacks. A particular flash loan attack is the pump and arbitrage attack in February 2020. So this is a particular attack where there was a flash loan transaction in a given block. The input to this attack was only $130 US worth of gas. So this was basically the capital that the adversary had to collect and use to carry out this attack. And the output of this attack was about $350,000, quite a sizable amount. So we will not go into all the details of this attack. We will discuss a second attack in a bit, but just want to show you like the general pattern of how a flash loan attack looks like. So we have here in the first step, there's a flash loan, right? So here the adversary took a flash loan on the platform DYDX. So the flash loan is actually free there, more or less free. It just costs like one way in fees to lend to get this flash loan there. And then there are a few operations, so we don't have to dive into details for this one, which obviously if you want as a homework you can do. But here I really just would like to show you that there are a few DeFi actions that are being carried out. For example, there's a lending action, there's a margin trade, there's an exchange, another exchange, and finally in this transaction the flash loan is being paid back. So what you notice here is that there are various platforms that are involved, right? So there's Compound, there's Uniswap, again Uniswap, there's BZX for the margin trading, and there's DYDX for the flash loan itself. You might also notice here that there are some pools like AMM pools, in particular the ETH and wrapped Bitcoin pool, where prices are being dumped here, for instance. And there's another Uniswap pool here where, the same Uniswap pool that's also affected here. So there's a second stage to this attack where there is an amount of Ether that's converted to wrapped Bitcoin, which is being done on Compound. So again, Kyber is involved here. So you see there are quite a few DeFi platforms involved. So the high-level message that I just would like you to gather from this particular example is that these types of DeFi attacks do basically involve multiple DeFi platforms in an atomic transaction. So this first transaction here is atomic, meaning that the actions 1, 2, 3, 4, and 5, they all execute either collectively or they fail. Right? And this very atomic property among different platforms is really something super exciting, super new, something we've not seen in the traditional finance domain. Just for the sake of this particular attack, so we looked at this attack in detail, and we found that the adversary could have chosen better parameters to carry out the attack. So by parameters, I mean parameters, for example, here, 10,000 Ether. Could we have taken more and made more money? We don't know, right? So there are a few parameters that could have changed. For example, here, how much do we collateralize? How much do we borrow? How much do we convert here? Etc. Right? So the idea is that given that you see such an attack on chain, you can model this attack and you can find out whether with an optimization framework, as we will discuss in a bit, you can find out whether the attack is executed in an optimal manner or whether the adversary left money on the table. So the second attack that we're looking at today is the BZX Oracle manipulation attack. So this was actually the second attack that was carried out on BZX in February 2020. So the first step of this attack is an adversary taking a flash loan on BZX. So BZX, we had in the earlier example, is a margin trade provider, but also performs or allows performing or allows borrowing a flash loan. So with the $7,500 US, the adversary basically takes 540 of this Ether, and he exchanges this on Uniswap, right? And he exchanges this to $, right? So this is the previous market price of ETH SUSD, and this is the market price after the adversary performs the trade. So you can see here that the liquidity in this Uniswap pool is not that high, right? So the exchange rate is significantly affected because we are adding here 540, so here 880 plus 540 is roughly this 1,420 ether. So the price certainly drops, right? So we have the initial exchange rate here as follows, and the price is clearly dropping here to 106 SUSD per ether. Then in the second step, what the adversary does is he goes to the Kyber reserve, which is another exchange, and in the Kyber reserve he sells, or she sells 360 ether for $, right? So again, we can see here the Kyber reserve had actually very, very little ether at the time and quite a lot SUSD, so very imbalanced, which is generally not very healthy either. But we can see here, this is the change of price. So we can see here as well that the asset price was dumped quite significantly, right, to 108.44 SUSD per ether. So now we know, okay, in this atomic transaction, given the flash loan, the adversary dumped the price of SUSD on the Uniswap and on the Kyber reserve market. So now, what the adversary does is the adversary would like to mint SUSD. And the thing is, the adversary still has quite some ether available. So the adversary uses 3,500 ether to create SUSD. And we can see here that now the adversary has quite some SUS dollar. The adversary can now go to BZX, right, which is a margin trading platform. And given this SUSD, the adversary can lend now ether at this platform. So we have about 1.1 million SUS dollar, which will give us almost 6,800 ether. So quite a significant amount in terms of ether. If you remember, we took roughly this amount at the beginning in the flash loan. The very important insight here is that BZX is using the Uniswap and the Kyber reserve markets as an oracle, right? As a price oracle. Like the BZX on-chain market somehow has to know what is the price of SUSD to ether, right? And because the adversary dumped the price of SUSD to ether on the Uniswap and Kyber reserve pool, which act as an oracle in the BZX platform, right, we naturally get a really good price for an SUS dollar. So you notice here that the adversary ends up with 9,800 ether, which is an incredible amount. And initially the adversary literally took, so if you go back here in the slides, only took 7,500 ether, right? So the idea of this attack was really this oracle manipulation, and naturally the adversary can then pay back the flash loan to BZX, which is minus these 7,500 ether, and we end up with over 2,000 ether in profit. So you might ask now, how do we optimize such an attack? So how do we find out what the optimal parameters are to execute such a DeFi attack? Well, what we can do is we can formulate the DeFi actions in models, right? I mean, we know that the constant product AMM, for example, can be expressed in this way here. And given the model, we can construct a constraint optimization problem based on the attack vector. So I'll give you an example just in the next slide. So the objective function, what that we want to maximize is the outcome profit. So what we do is we fetch the on-chain state that the attack is expected to be executed on, and then given the on-chain state, we can optimize the parameters. So let's look at how this would work for the BZX attack 2 that we just discussed. So we have an initial borrowing, right, and an end repay. So we have a borrow flash loan and a repay flash loan at the end. If we don't pay back the flash loan, the transaction would fail. Hence, we have to naturally pay back. So what's being done in the first step is that we have a parameter 1. We don't know how many ether we want to provide to Uniswap, right? So there's a certain function of this P1 of SUSD that we want. The second parameter here is how much Ether are we going to contribute to Kyber. So you remember Uniswap and Kyber together are the price oracle for BZX. The third parameter that we are looking at is how much do we put into synthetics to mint as US dollar. And then how much Z as US dollar should we borrow, should be used to borrow G of Z Ether on BZX itself, right? You remember this was the last step. So BZX, here this is BZX. BZX is basically using Kyber and Uniswap as a price oracle. So we can exploit, in a sense, the fact that BZX relies on this on-chain markets that we can so easily manipulate. So putting all together, we have here this function, and we have the following objective here that we want to maximize, right? And naturally, P1 plus P2 plus P3 has to be smaller than X Ether. So that's the maximum amount of Ether that we can lend, that we can borrow as a flash loan from the BZX platform. Naturally, we can choose any other type of flash loan platform. It doesn't have to be BZX. I just followed in this particular example what the adversary has done before. So this, you can basically throw it into an optimization algorithm. So we have used the sequential least square programming algorithm, which is available in SciPy. We have executed this on an Ubuntu 18/16 CPU cores, 32 gigs of RAM, rather small machine, and we then validated this by concrete execution on the real blockchain. So if you would like to do this yourself, you can use, for example, Hardhat to fork the chain at a particular height. So I hope this gave you a good introduction how a flash loan attack is possible. Recall, flash loans are really just a tool for you to carry out the attack. Maybe think for a little exercise of how would you prevent such an attack, right? So this was an oracle manipulation. Well, if your DeFi app is relying on a market where the price can be easily manipulated through a flash loan, then maybe that's not the safest. So you might want to use additional oracle sources. Uniswap also now provides a time-weighted average price, which should be less manipulable by an adversary. But this remains a rather difficult kind of challenge to secure DeFi protocol, because the state of other protocols might be dependent on yours, and an adversary might be able to create such a market manipulation attack. Welcome back. We're now going to discuss sandwich attacks. Sandwich attacks are one of the really predatory trading techniques whereby you front and back run a victim, and the victim is in the middle. It's a juicy transaction, victim transaction, hence sandwich. Let's dive into it. So sandwich attacks are particularly applicable to automated market makers. So we've covered automated market makers, short AMM, in an extensive lecture. Just a very brief recall, right? You have, for example, in the constant product AMM, you have an asset quantity of X, and you have an asset quantity of Y. The product of those needs to remain constant while you're trading with the AMM market. A sandwich attack is then really literally a sandwich whereby you have a victim transaction. The victim transaction is exchanging as an asset X for an asset Y. And we have here on the x-axis the time appearance on the blockchain network. So after a victim transaction was observed on the network, right? So here the victim transaction started propagating. An adversary is creating an adversary transaction 1 that should be front running the victim, and an adversary transaction 2 that should be back running the victim. So hence here this is the victim and this is A1, the adversary 1 and adversary 2 transaction, right? So the idea of this transaction is that the adversarial transaction A1 will manipulate the on-chain market that the victim transaction will transact on. So the adversarial transaction will try to squeeze as much financial profit out of this victim transaction as possible. So let's look at how this is how this works and why and how much technically could be extracted from a victim transaction. To fully understand sandwich attacks, we need to go back to the very basics of a constant product formula, or AMM in general. So on the x-axis here we have the amount x of asset x, and on the y-axis we have the amount y of asset y. I hope you remember. So if we have a state before that's, for example, 10 and 30, so 10 units of asset x and 30 units of asset y. So our constant k would amount to 300 in this particular example. So now we're gonna trade. So we're gonna remove here minus 10 assets. So basically we want to retrieve from the pool 10 assets, right? So on the curve we're gonna be here. So now the question is, how many assets do we have to provide to this pool here, right? Somebody remembers or maybe recalculates based on these examples, please leave a message in the chat. Very right. So we have plus 5 here, right? So we need to provide the pool 5 assets in order to be able, 5 assets of X in order to be able to take out 10 units of asset Y, because the constant K remains constant, and that's the constant product formula, right? So now the number of coins here that we get back, basically the exchange rate, right, is really determined here by this curve, right? I mean, by the points on this curve. So every coin that we get is basically not precisely the same price. So obviously there's an average price that we get, but the more we trade, the more expensive the trade becomes. So here there's basically an expected increase or decrease in price based on the trade volume and available liquidity in particular. So the curve here is describing the expected increase in price. So the longer you go along this curve, right, the more you will pay per coin that you purchase. So the idea is that the pool should not be easily drainable, but you should always have instant liquidity. That's one of the properties of an AMM. Now what can happen is that you can have some transaction that front runs you, right? Whether it's a benign front run or malicious front running, and you suddenly your transaction is executed here at this point, or starts to be executed at this point of the curve instead of the other point at the curve that you anticipated earlier. So what can happen is that if you execute here, you would certainly get a worse execution price. Also, on the other hand, you can, if you're front run by a benign transaction that trades in the other direction, you could end up getting a better price, right? So it goes both ways, really. What's really important, however, is that you want to configure a slippage protection to prevent any unacceptable slippage that you might be exposed to. So this goes, or I mean, I guess the closest analogy would be a limit order. So in a limit order book, you say I'm willing to pay at most the following price, right? So the slippage protection in essence is really similar. However, the way you specify it, for example, on Uniswap, is by clicking on this little icon here currently in the UI. And then you can, for example, specify 1% or 0.1%, or Uniswap also has an auto setting. So I'm not actually quite curious of how this auto setting works. So if you have any ideas, or if you have maybe checked this out, please leave a comment in the chat, because it's quite crucial how this automated slippage setting works, because the more open you are to slippage, the more likely you will be a victim of a sandwich attack. So I would I would much rather prefer this to be a static and smaller number, but it's true that if this number is too small, then if given a volatile market, it could happen that your transaction keep failing because the price just changed inherently in the market. Hence, you do need some slack in the slippage setting. Now let's go back to the slippage protection and when it actually triggers. So here you can see that we have somehow a transaction that was front running us, and we wanted to purchase this amount of liquidity. Now it turns out we actually crossed the slippage protection threshold, right? So no luck here, and basically this means that that the transaction failed or will fail because we crossed the limit that we specified earlier. So we will be liable to gas fees or transaction fees to the miners, but at least we won't overpay on the asset price because we don't go over a price limit. Okay, and here again, right, you can specify the limit in the Uniswap UI. So now let's put all the elements together, right? We do have, for the sandwich attack, so we do have a victim, and we do have an adversarial transaction that's front-running the victim. So in this visualization here, you should see very beautifully that here, this very point, right, the victim is really being pushed very closely to the slippage protection threshold, but not beyond. If the victim is pushed beyond the protection, it would fail. We don't want the victim to fail. We want the victim to execute, but we want to kind of squeeze out here this amount of or push back the price to the worst possible price that the victim is willing to accept. And in the second step, the adversary can cash out by basically doing the reverse trade. So the idea is really to maximize the victim's slippage during execution. So this is the unexpected slippage that the victim will suffer from. So to execute such a slippage attack, we look here at the following architecture, let's say adversarial architecture. So we have here the victim V, right? It just creates transactions, broadcasts in the network, and then we have an adversary with a SPI node. So remember, SPI node is a node that is very well connected in the network, and it receives data really early on. So it just sees most of the transactions very early on. Based on the transaction data, it can find out what's the slippage protection threshold. Hence, it can calculate whether it's profitable to execute a sandwich attack. And if it is profitable, then the adversary will create a front-running and a back-running transaction, broadcast these in the network, which will be added to the miner's memory pool, hopefully before the victim is mined. And if the adversary is lucky, he will get all the 3 transactions included in the same block, ideally very close to each other. Right? And this is one of the possible ways to perform a sandwich attacks. There are a variety of variations of these attacks. We will show you one in one of the following slides, but this is really the very gist of it, right? You act on public information that you see in for example, the P2P network. You push a transaction to the limit and then cash out back on it. So you might ask, is this attack always profitable? Well, the good news is that it's not. So here you have a plot that we derived. So you have here on the x-axis, you have, for example, the ether transacted by a victim. So this is on a particular Uniswap market that we took actually as an example from Uniswap. And obviously these numbers may change at any point in time depending on the market state. But let's assume here we have ether, the number of ether transacted by the victim. And here we have the ether transacted by the adversary, right? So you see a victim transaction. For example, you observe a victim transaction that trades 20 ether. you have set a slippage protection of let's say 1%, right? Which seems to be one of the default options in the Uniswap market. In the Uniswap UI, then you can see here that the adversary would need a little bit more than 22.5, probably 23 Ether to attack the victim. And what's interesting is here we are in the green area. The green area represents the revenue that the adversary can extract. And you can see here we're roughly on the area of 0.2 Ether, which is not bad for a single sandwich attack, right? So keep in mind, if you have here, for example, a slippage setting of 0.1 Ether, then we're just about here. Then the adversary has almost no chance of extracting any significant revenue here. So far, we've only looked at one particular adversary attacking a victim, but naturally the blockchain environment is an environment where we have many adversaries, and it's a very competitive endeavor there. So if we've tried to understand if we have multiple adversaries and they will basically try to outcompete each other, so the longer the victim transaction is pending in seconds here in the Ethereum network, up to 30 seconds and up to 10 adversaries, we try to simulate what's the gas price that will evolve, right? And what's the break even? How hard the break even becomes. So we can really see here that the gas price becomes incredibly high in terms of gigawatt. So this is a counter-reactive bidding. So it means basically I see a victim, then I perform a sandwich attack, then another adversary sees my sandwich attack, I perform a sandwich attack by bidding higher prices. So it gets very competitive very quickly. A particular advanced sandwich attack would be where a liquidity provider attacks a taker. So far what we've looked at is that a taker attacks a taker, so a trader attacks another trader. But in an AMM, we do have liquidity providers, or LPs for short, right? So they add and they remove liquidity. So there may be settings where an LP can actually, here, for example, remove liquidity or add liquidity, and then do the reverse operation just to squeeze the victim into a worse price, right? So, and these are settings that are certainly interesting to explore, and we haven't seen much quantitative analysis being done on this angle so far. So I hope you really liked sandwich attacks. These are very juicy burgers in essence, with juicy victim transactions that can be exploited. Very creative attacks. Also, the liquidity providers can probably attack the liquidity takers, or maybe a liquidity provider can attack a liquidity provider. So I'll leave it up for an exercise for you to find out maybe some more varieties on the different attacks. Welcome back. We're gonna now discuss blockchain extractable value. What is blockchain or miner extractable value? Well, let's look at a concrete example. So if the price of the collateral of an asset drops below a health factor, right, as you maybe recall from our lending lecture, then there is the event, there's a possible event of a liquidation that a third party can trigger. Now the question is, who will liquidate? Is it the miners? Is it just a regular user? Or is it some kind of an adversary that tries to front run other users? So there are variety of sources on how to measure miner extractable value. So you can, for example, check out flashbots.net. They have a dashboard and their own data and their own metrics on how to extract data. We have also come up with our own metrics and heuristics on how to extract the value. In particular, we have done this for example, sandwich attacks, right? So we have looked at the monthly profit and the number of sandwich attacks here starting in in December 2018, going back until almost here August 2021. So over quite some time frame, we've tried to, based on the blockchain data, we've tried to understand how are the different or how much sandwich attacks are actually happening in the real world. So keep in mind that the y-axis here is a log scale. So a small increase in particular here might correspond to quite a significant financial amount. So you can see what's interesting is here that Uniswap version 3, for example, was just introduced here. And then in the month after, the Uniswap sandwich attack amount already was rather significant, right? And has been growing since then. You can see here we have basically looked into Banco, Uniswap version 1, 2, and 3, as well as SushiSwap. The number of sandwich attacks have also significantly increased, as you can see here. This is just the very raw number, with attacks hitting as much as 100,000 sandwich attacks per month on a particular market, on a particular exchange, not market. So this is basically taking into account thousands of on-chain markets. Another source of miner extractable value is liquidations, right? So liquidations is the event whereby if you have a collateral that the price of a collateral which drops below health factor, then you do have the liquidation event. So here again we looked from 2019 until August 2021 at the most important lending platforms on Ethereum, and we have found here that there are quite a variety of liquidation events. So keep in mind we have only looked here at the fixed spread liquidation, so these can be done atomically in one transactions. For example, the MakerDAO liquidation mechanism, at least in the past, was based on an auction setting, so this was not an instant liquidation. So we captured here those that can be performed in an instant atomic transaction. Hence, these are things that miners can actually extract, right? So a miner can reorder transactions and hence extract liquidation revenue. And finally, the third category of miner extractable value that we try to quantify is just plain old arbitrage. So again, here this is from 2018 until August 2021. So we have here as well the number of arbitrage attempts are likely higher, slightly higher than sandwich attacks, and also the revenue here you see has been growing quite significantly. So notice that we have included additional markets such as Curve and Swerve in this particular evaluation, as well as 1inch. Right? So arbitrage is naturally seen as a very benign trading strategy to help the markets become more efficient, but there's certainly a type of a cost associated to perform arbitrage, like on-chain overhead, and this is certainly something that miners can extract if they would like to. Thank you very much for listening. So I've introduced a variety of sources of miner extractable value, because miners have the authority to instantaneously and single-handedly order transactions within a particular block that they mine. So they technically have access to all this additional revenue that you can source from the blockchain. So traditionally you had only the block reward, the transaction fees. Nowadays, on top of this, you have the miner extractable value. Welcome back. We're gonna now discuss transaction replay attack, or more specifically generalized transaction replay attacks. The idea of a replay is really to create kind of a copycat of an existing transaction. So replay is a technical term from a traditional network security environment. And the idea is to observe a transaction on the network layer. Then you do replace certain data, you sign it with your own private key, and you broadcast the copy. So it's really just a copycat behavior. So the potential profit that we identified is about $35 million over 32 months, over a 32 months period. Naturally, what we have ignored here is the possibility that others will front run you, or front run your copycat, or defend against being front run. So we've gathered about 188,000 profitable transactions over these 32 months of historical blockchain data, and this represents about 0.02 of the entirety of the Ethereum blockchain transactions that we have seen. We've developed a real-time algorithm which is not very much optimized, and which could even be parallelized, but we basically can replay a transaction in less than 0.2 seconds, as we report here. So I'm sure you're quite curious now, and how does this algorithm look like? Well, it's really very simple. So what we have here is we have a potential victim transaction that you can see here, right? This is being basically injected into this algorithm. And we have here an adversarial address, right? So a victim transaction adversarial address. And the adversarial address is replacing the sender address. At the same time, in the transaction input, we are searching whether the victim sender address is present anywhere in the input, and if it is, then we do replace the input with the adversarial transaction. And that's really it. So what we do find is that here on the x-axis we have the timeline that we evaluated this on the Ethereum blockchain, and on the y-axis we have the accumulative profit in Ether. So you can see here that the block top replayable. So for those blocks where we can, if we replay it on the top block, then we can get probably over 50,000 Ether within those 32 months period. So naturally, the amount of US dollar that I reported earlier is based on the Ether price at the time of the measurement. So what we can basically observe is that the accumulated profit that can be extracted by replay attack is really significant, right? And the number of replayable transactions remained more or less constant while still being rather volatile. So we can see here there's some coarse-grained volatility on the number of replay transactions. But we do observe about 15,000 transactions at most per month that can be replayed. So that's certainly also a common issue in trying to secure DeFi protocols. So Sam, for instance, might have told you that or ways on how he tries to protect his transactions from being replayed by automated or generalized front-running bots. So this particular algorithm here that we show you is really a very simple one. I'm sure there are tons of much more sophisticated algorithms out there, but I just wanted to show you that even with this simple algorithm, if we do evaluate it on past blockchain data, we can find quite some significant value extraction. Very good. I hope that you enjoyed this replay algorithm. So please be aware, if you're issuing a transaction and this might extract some value that others could copycat, well, try to protect yourself, right? There are a variety of different ideas on how to do that. You can create a more complicated smart contracts that can't be replaced as simple as easily as through the algorithm I've shown you. You could have private peering agreements with miners to let them help you to extract the value that you want without being replayed, but at the same time you will have to trust the miner not to replay you. So it's a tricky game, but it's fun. Welcome back. Well, we've discussed very extensively what MEV is previously. I might have not been crystal clear with you of why it matters to security. And in this segment of the lecture, we'll be discussing BEV forking, or miner extractable value forking, and chain reorganizations. So the dangers of naively maximizing MEV, or basically extracting MEV, is the following. So let's assume we have here a block B1, right? So this is a particular block, and let's assume that there's an honest miner, he or she mines block B2, and there's an MEV opportunity in this very block. There might also be a malicious miner, and this malicious miner would like to extract this MEV opportunity, right? So now the question is for the honest miner, well, the honest miner would like to continue mining on B3, so this is certainly one case, but this means that the malicious miner will basically forfeit the previous MEV opportunity. And why would the miner do that? Why would the adversary just give this MEV opportunity to this honest miner of this other block, right? Doesn't make much financial sense. It's not very rational. It's not a very rational thing to do. Well, depends at least on the value of the MEV opportunity. So naturally here it might happen that the adversary keeps mining on block C2, because this is the rational thing to do in order to attract the most value out of the block mined. So you can see here the MEV miner or the adversary miner basically extending C3 instead of continuing on the honest chain B2. So, and then again, right, there might be the case, well, the malicious miner could mine on C4 to continue increasing basically its chain, and the honest miner could continue on B4 or on C4. So that's really up to the honest miner. But overall, the message, the high-level message here is that this MEV opportunity, right? This opportunity here creates a competition among miners to include this very opportunity. Because it could be mined in any block, but it can only be mined in a single block, not in multiple blocks at the same time. So what we observe is there's a potential waste of computational power, which then increases the stale block rate, and this increases the risks of double spending and selfish mining, two very security relevant concepts that we have discussed in this lecture already. Now what you can do is to quantify how important this threat of miner extractable value actually is. You can quantify the optimal adversarial strategy in for example, a Nakamoto consensus blockchain. So what related work has done is to instantiate a proof-of-work blockchain with various network and consensus layer parameters to extract the stale block rate. So as you might know, the stale block rate in Bitcoin is on the order of 1%, depending on the state, obviously. In Ethereum, the stale block rate was measured between, I think, 5 and 7% so far. But please don't quote me on that. So this is roughly the order of magnitude that I'm aware of. And what we can then do is we can model the blockchain as a Markov decision process. So a Markov decision process is a special instance of a Markov chain, but with an added action and state space. So, and there we can instantiate a few attacks, for example, the selfish mining or the double spending attacks that we've discussed earlier. And the Markov decision process, when you solve this process, you will get a set of optimal strategies to perform depending on the state. So this is the output basically of the Markov decision process. So what I would like to show you is really how to model a blockchain in an MDP, in the Markov decision process. I think this is probably the most interesting takeaway message for this segment of the lecture. So let's assume here we have an honest chain, right? So this is just a regular honest chain where a transaction pays a vendor. So, and let's assume that in parallel, an adversary is mining a secret chain here, this red one, which is not public yet. And there's a transaction that pays the adversary. And this transaction is a double spend transaction, which is in conflict with the green transaction, right? So these two transactions here, they cannot be mined together at the same time in the blockchain because they're conflicting each other. So in an MDP, what we can now do is we can model the adversarial chain here as the length 3 and the honest chain as the length 1. So 3 is the attacker chain, 1 is the honest chain. And the adversary now can choose an action. So the adversary can choose what to do. So let's assume that the adversary will override the honest chain. Overriding means the adversary will publish 2 blocks, so B1 and B2 prime, right? And because B1 and B2 prime are a longer chain than B1, this will override the main chain. So the main chain is now this construct here, and it's no longer this one, right? This is overridden. It's no longer a valid longest chain. And naturally now the honest network will continue mining on B2 prime, but the adversary got a profit, right? The adversary got the block reward for these 2 blocks plus the double spend reward for this very transaction. Well, at least as long as the miner accepted here the transaction after 1 block confirmation. But what you can see is here we have a state space, right? This is like 3-1 in this particular case. We have an action space. So we had the action override, for instance. The adversary could have also waited. This is another action. And we got a reward that we can specify. So the reward was 2 block rewards plus a double spending value. Right? So I think this is really quite a cool tool to model how a blockchain would operate. And once you have this model, you can always plug in additional parameters, additional rewards. And we try to quantify to what degree miner extractable value would affect the security of a chain. So what would be the optimal strategy for a miner to perform mining in the presence of a miner extractable value reward? So we have done this quantitatively, which you can see in this particular paper. But what we have seen, so just to give you an example, is that if given a 10% hash rate miner, right, which is it's a big miner, but it's not like the biggest, right? If there's a 4x average block reward, I mean, if there's an MEV opportunity that's 4x the average block reward, then this 10% hash rate miner will be incentivized to fork the chain. And this is really this is dangerous because we will see through. I mean, if the miners are getting more aware that this can be performed on the mining level, right? If you can basically design an algorithm, I mean, for example, with SMDP, you could design an algorithm that selects your optimal adversary strategies. And you automate this in the mining software, for example, in Geth, then we might see many more state blocks, and the chain security will significantly deteriorate. And this example is just like a small miner with 10% and a 4x block reward MEV opportunity. And alarmingly, what we have seen is like MEV opportunities beyond 800x the block reward. So you can imagine what would happen. Thank you very much. I don't want it to make you afraid, but MEV is a security concern, and it's not wise to ignore the dire consequences of rationality, especially once miners have potentially access to automated forking software that is like optimally designed. So an MDP might be one avenue towards this goal. It's certainly not flawless, but yeah, we should be on the lookout and try to minimize MEV and prevent security dangers on our well-advancing DeFi ecosystem. Welcome back. We're gonna now discuss the new emergence of miner extractable or BEV relayers. So these are centralized front-running as a service infrastructure given by variety community members. And we're gonna discuss also possible options of how to mitigate MEV, which is such an important topic to increase blockchain security and make our entire DeFi ecosystem more sustainable. So BEV relayers are really these centralized entities mostly servers, actually, run by individuals or companies that attract, on the one hand, so-called searchers. So these are third parties that are crawling the blockchain for and the network layer for miner extractable or blockchain extractable valued opportunities. So they create, so basically they look at the blockchain or look at the network layer and they create these extracting transactions. And what they do is they do bribe miners. So they pay a fraction of their revenue and they do pay them to miners. So we've looked at a little bit of data, and some of them pay like over 90% of the extractable value to miners. So, and this BV relayer, which is just the centralized service receiving these transactions, is then forwarding them to miners. And the miners are running a custom Geth client to sort basically these transactions and then mine the transactions that are the most profitable there. So they will basically be put in the first block positions. So it's quite important to note that this BV relayer may mitigate denial of service attacks against the miners, but technically you could have like a direct link here to a miner instead, right? And I mean, why have middlemen in a blockchain environment, right? If all that we do is really to strive towards eliminating the middlemen. So I would advocate for more decentralized approaches where the searchers, for instance, would directly speak to the miners instead. The other issue is that the existing BV relayers that I'm aware of, they can censor reorder transactions and they can actually mine the transaction information about what these searchers are doing. So these searchers are, in most cases, really smart individuals creating very nifty strategies on how to extract financial value. While we don't really know what the agenda of these BV relayers is, I would also encourage you to ask these BV relayers what are their terms and conditions, what are their privacy policy, etc. Right? So I've tried to understand this domain a little bit, but there doesn't seem to be much transparency, to be honest, which is quite an issue, I think, especially in a decentralized system. So please be aware of these possible concerns. So I've written them down here for you to digest in detail. So we have seen that miner extractable value, or BEVs, provably incentivizes miners to fork. So this was published at Security and Privacy this year. It's a real security concerns. We're seeing that the BEV relayer server centralized the peer-to-peer network, right? We don't know what these relayers do. They may resell the profit from searcher strategies, or they may not actually necessarily reduce any peer-to-peer overhead. Although I've seen this being advertised as one of the main sources of why BEV relayers are useful. It may also be a concern that the for-profit company that is running these relay services distributes a Geth client to over 50% of the miners. So the Geth client development should ideally be decentralized. But if we have a centralized company creating the relay server as well as patching the Geth client, then the Geth client is being provided to miners from a single source, which is a danger on the decentralization aspects. And last, but probably the most important, is that these BEV relayers maximize MEV, so they maximize the extraction from, for example, sandwich attacks. And this means that whenever you trade, they will try to extract the maximum slippage they can from your trade. And I doubt that's something that's aligned with your incentives. So what can we do to protect ourselves against MEV? What's the anti-MEV solution space? So there are a variety of great ideas, but it's still a long way to go, I believe, to really protect users as a whole. So there's quite an emerging and really interesting body of work going into the fair ordering on the blockchain layer. So this is by Ari Jules, who gave the Oracle lecture. I can really recommend you to look into the Equitas protocol family. We might be able to fix MEV at least partially on existing dApps. So what we can do is we can merge AMM DEXs into one. So we can build an on-chain aggregator, as we discussed in the DEX lecture. We can design MEV mindful dApps, so we can try to minimize the MEV by design. For example, if there's a price Oracle update in a liquidation platform, maybe this Oracle update immediately performs a liquidation instead of leaving that opportunity to others, and the liquidation proceeds can then be distributed to some, for example, token holders or something. I believe there's quite some interesting design space to protect from MEV. But the entire story gets certainly more complicated with cross-chain MEV. So we are effectively living already in a reality with multiple chains, where cross-chain MEV can be observed already, and certainly this is even more challenging than to fix. So even a fair ordering on one blockchain layer might not help fix cross-chain MEV opportunities. So just to dive a little bit again into the application-specific MEV mitigation techniques. So I would like to show you here this particular example where we have two markets of the same coin X and Y. So if we have a trader who then swaps X for Y on that market, well, naturally the price of X declines, right, on that market because we're selling X. And now we have multiple adversaries that actually observe this particular transaction, probably already on the network layer, and they will anticipate then to arbitrage out this very market change, because this market here needs obviously to be synchronized after the user has performed a swap on that market. And if there are multiple adversaries or arbitrage entities performing this synchronization, then there's certainly an overhead in terms of network congestion, right? So we have observed background flooding on the network layer, we have observed price gas auctions, and overall then the transaction fees gets increased for the users. And moreover, the user itself forgoes an arbitrage opportunity, right? So wouldn't it make just more sense if the user instead goes through a smart contract that performs optimal routing and arbitrage and naturally divides the assets among those markets instead of leaving the profits to third parties that will anyways increase the overhead on the chain? Well, it's still to be seen. I believe there are many opportunities in order to build a more sustainable and safe blockchain, DeFi blockchain environment. Thank you so much for listening. It was really exciting to dive into the variety of security-related topics for DeFi. Please don't hesitate to ask any question, whether it's in the chat, in the group, forums, or in the Discords, etc. We're here to help you understand DeFi security in and outside.